So the first reaction that we're going to examine is the E1 elimination reaction. So E1 is a unimolecular elimination reaction, just like an SN1 reaction is. And in the case of the SN1 reaction, this elimination reaction is a competing mechanism. And of course, it follows still the same unimolecular rate law um, that an SN1 reaction is called. And so we call it an E1 reaction. The rate of an E1 reaction is identical to the rate equation, I should say. The rate equation of an E1 reaction is the same as the rate equation of an SN1 reaction. Not saying that the rates are the same, but the equations themselves are the same, being that the rate simply depends on the substrate with the leaving group, the alkyl halide or alkyl tosylate, right? So, for example, if I take a tertiary substrate, so here I have tert-butyl substrate with some leaving group. In an SN1 mechanism, we see that the leaving group comes off and you form a carbocation, in this case the tert-butyl carbocation. Now, for that SN1 mechanism, what happens? Well, we bring in some nucleophile. So here's a nucleophile. Maybe it has a negative charge, maybe it doesn't. For most SN1 reactions, we saw that the nucleophiles were actually pretty weak nucleophiles, weak bases, solvolysis reactions, and therefore the nucleophile was actually a neutral compound. But for simplicity, I'm going to say, okay, I have some nucleophile with a negative charge. And we see that it attacks that carbocation, and we get what we call substitution, right? The nucleophile has substituted for the leaving group. That's what we learned in the previous chapter. Well, now we're going to find that something else can take place. Certainly, the leaving group can still come off, and in an E1 mechanism, that's exactly what happens. The leaving group comes off, but now something unique happens. And I said in the previous video that when a vicinal carbon, a beta carbon, undergoes elimination or has a hydrogen to it, right? So we're reacting some nucleophile, but now the nucleophile is a little bit maybe more basic, or maybe it's the same nucleophile, but it's going to, instead of acting as a nucleophile, it acts as a Bronsted base. And we have this beta carbon with a hydrogen, and so now that nucleophile, instead of attacking the carbocation, it's going to attack the beta hydrogen. And what happens is, when it does so, the electrons from that carbon-hydrogen bond go to form a pi bond, right, between carbon, that beta carbon, and the carbocation. The result is that you now have an alkene, right? So I formed a pi bond. And this is what is often referred to as beta elimination. Why beta elimination? Because you've eliminated a hydrogen on a beta carbon. And that's important to understand. You'll hear me occasionally use that terminology, beta elimination. That's where that comes from. So a vicinal carbon or a beta carbon can lose a hydrogen in the process. The mechanism looks very similar. The potential energy diagram actually looks fairly similar between an E1 and an SN1 mechanism, and this is one of the reasons why these two mechanisms compete with one another, because of the similarities in their potential energy diagram. Now, there are some differences, and we'll get into that in just a little bit, right? So here is an example. I take tert-butyl bromide and I react it with ethanol at 25 degrees. Now, in the previous chapter, we'd say, okay, this is a substitution reaction. I have a tertiary alkyl halide. I have an alcohol, so this is ethanolysis, right? A solvolysis reaction. And we would expect to see a substitution reaction, and this would be the substituted product. We would form an ether. And now we're adding an extra component to this, an extra layer of complexity, in saying that, well, that's not all that is not the entire possibility for product formation. Another possibility is that I can simply eliminate one of the beta hydrogens. In this case, all of the beta hydrogens are equivalent, and so I would get an elimination product, an alkene forming as well. Now, if I look at the product distribution, I see that my substitution product is still the favored product. I get an 80% yield and only a 20% yield of the alkene. And therefore, well, I'm favoring substitution. So nothing really is new based on what we have discussed in the previous chapter, right? I'm still getting substitution as the major product. However, if you look um, at the difference in energy between the substituted product and the alkene, you see there is a slight difference. With the substituted product, the ether on the left, I have all carbon-carbon single bonds and carbon-oxygen single bonds. With the product on the right, my alkene, I'm forming carbon-carbon double bonds. And we know that that double bond provides more stability to the molecule. Alkenes are more stable than simple single bonds. So double bonds are more stable than single bonds. Well, what's going on there? Well, you see that in this particular case, the pathway to get to substitution must be a little bit lower, but the product formation is less stable. So this is driven simply by kinetics. We have the alcohol attacking the carbocation, unstable carbocation, and therefore that process must be a little bit faster than an alcohol removing a beta hydrogen. Well, how can we promote the formation of the more stable product? Well, we can raise the temperature. And so we see that at higher temperatures, you tend to increase the formation of alkenes because alkenes are usually more stable. And that is how one way that we can tweak this system to promote the formation of the alkene. Even with a very weak Bronsted base, alcohols are weak Bronsted bases, we can see that we can get more and more formation of the alkene if that's what we want. But at low temperatures, we can get good yields, relatively good yields of our substitution product. So here's an example where we have again, this is a tertiary alkyl halide, and it's reacting with methanol. Again, we would say this is SN1 substitution mechanism, right, from the previous chapter. And indeed, we get a substituted product. We get our ether formation. But we can also now form an alkene. And so now we're adding, again, that extra layer. And so now if I say, well, what's the product or products of this reaction? You need to look at both substitution and elimination. And then toward the end, we're going to get into, well, which one's going to be the major product. And certainly with this reaction, it's going to depend on the temperature. Notice I don't give a temperature here. And so you simply say, well, I'm going to get both products. I don't know what the product distribution is based on the temperature. But if I give you a low temperature, you can expect substitution. And if I give you a higher temperature, you can expect to get more elimination. And that's kind of how you know, the general trend of elimination versus substitution is going to be. There's a little bit more complexity there, but most of the time when you increase temperature, you're going to increase alkene formation. Now notice in this particular example, the substituents coming off of that alpha carbon, the carbon with the bromine attached to the bromine, I have 3 ethyl groups, and all of the ethyl groups are the same. So that if I remove a hydrogen from a vicinal carbon, a beta hydrogen, the product is always going to be the same. But what happens if the substituents coming off of that alpha carbon are not the same? Well, this brings us to what we call regioselectivity. Regioselectivity. In many elimination reactions, there is more than one hydrogen that can be removed. And this simply leads to different product formation. So, for example, if I have, so this would be 1-bromo, 1-methyl cyclohexane, and I treat this with methanol. Again, a solvolysis, we're going to be promoting SN1 and E1 mechanisms, SN1 and E1 mechanisms. So the bromine's going to come off, right? And I'm going to form a carbocation. And that is going to be a tertiary carbocation. But notice I have two sets of hydrogens here, of beta hydrogens. So I have these beta hydrogens, which all four of these hydrogens are the same. And then of course, I have the three hydrogens on the methyl group. So these three hydrogens. And notice if methanol as a base, a Bronsted base, removes any one of these hydrogens, I'm going to get two different products. So if I remove one of the blue hydrogens, I get this alkene. And if I remove one of the green hydrogens, I get this alkene. Again, keep in mind, I'm also going to get substitution, so I'm going to form my ether, but I'm simply not showing that here. What I'm showing is I'm highlighting the distribution of the alkenes, the product distribution of the alkenes. So number one, I'm going to get two possible alkenes, right? Because I can remove any of those hydrogens. So in removing the blue hydrogens, I get one alkene. In removing the green hydrogens, one of the green hydrogens, I get the green alkene, right? And we see that based on what's called Zaitsev's rule, or sometimes you'll see it spelled like this, Zaitsev. It's kind of interesting. Zaitsev was a Russian chemist, but he, during the communist revolution, Russian chemists weren't really allowed to publish anything. So what Zaitsev did is he sent his manuscripts over to Germany. And the Germans translated his name as Zaitsev because they only heard him speak his name, Zaitsev. And that's how he pronounced it, Zaitsev. And then later on, it was discovered he spelled his name Zaitsev, but it's pronounced Zaitsev. So in some textbooks, you'll see it spelled one way, in Jones, you see it spelled with the S. In other textbooks, you see it spelled with the Z. So Zaitsev's rule states that the more substituted alkene will predominate. Why? Because it is more stable. So the more stable alkene is going to predominate. And therefore, we again have to think about substitution patterns, right? What degree of substitution does the alkene have? And if you look at the alkene on the left, the blue alkene, you see it's a tri-substituted alkene. If you look at the alkene on the right, the green alkene, you see that it is a di-substituted alkene. And therefore, a tri-substituted alkene is more stable than a di-substituted alkene. And so we would expect to see the product distribution giving the major product as the tri-substituted alkene. So that is what we refer to as Zaitsev's rule. Okay? All right, so let's take a look at dehydration. Now, dehydration is one of the most common E1 reactions that we're going to talk about. And it's a little bit different than your typical substitution reaction because it involves an alcohol. Now, remember, we said that alcohols are poor leaving groups, but we also saw how we can promote the loss of that OH by protonating it. And what we discover is that alcohols can be protonated by an acid whose conjugate base is a very weak nucleophile. And when that occurs, you don't get substitution. You actually promote elimination in that process. So what kind of acids can we use where their conjugate bases are very weak nucleophiles? Well, there are two very common acids that are used, sulfuric acid and phosphoric acid. So whenever you see an alcohol reacted with sulfuric acid or phosphoric acid in a little bit of water, now that's the key. So generally speaking, you simply add the alcohol to sulfuric acid or phosphoric acid. Sulfuric acid is 98%. There's some water present in there. Phosphoric acid is about 70%. There's 30% water in there. And what happens is, of course, once you protonate, you now have water as a good leaving group. And then you have no really good nucleophile. You have the conjugate base, so you have hydrogen sulfate or dihydrogen phosphate as the nucleophiles, which are very poor, and you have a little bit of water in there, which is also a poor nucleophile. And as a matter of fact, it just came off, right, as a leaving group. And so what ends up happening is you get a reaction that looks something like this. Oh my gosh, look at what happened there, right? So I take a simple alcohol, 2-butanol, I react it with sulfuric acid with a little bit of water. Keep in mind, when you see that water, it's actually not being a solvent necessarily. It's just present in there. And you get 3 different products. So here there are 2 beta carbons, and so I can get elimination to give me 1 butene. I can get elimination to give me 2 butene. Notice with 2 butene I can have either cis or trans 2 butene. And we're going to look at how we form these 3 products, right? So how do we look at understanding how these 3 products are formed? That's right, you have to look at the mechanism. So what's happening here? Well, we're taking our 2-butanol and we're reacting it with a hydronium ion. Now, where does a hydronium ion come from? Remember, the hydronium ion is coming from sulfuric acid reacting with a little bit of water in there. The hydronium ion is the acid that is involved in this reaction. So now what happens? Well, I'm going to get an acid-base reaction taking place. So I'm going to get a proton transfer occurring. The alcohol is going to deprotonate the hydronium ion, and I form my oxonium ion plus water. So now what's going to happen? Well, the oxonium ion is now, the water is a good leaving group, and so that water can come off, and now I form a carbocation. So this is a secondary carbocation, and I have to look at what's taking place here. Well, water can come back on, and obviously there's an equilibrium process that's occurring, but water can also act as a base, and so it can remove a vicinal hydrogen. Where are the vicinal hydrogens? Well, you see that there are 2 types of vicinal hydrogens. There's the blue, the vicinal hydrogens, so the hydrogens from the carbon on the left, and there are the hydrogens from the beta carbon on the right, so the blue hydrogens or the green hydrogens. Now, when I remove one of the green hydrogens with water, right, so I deprotonate it, and the electrons from that carbon-hydrogen bond go in to form a pi bond with the carbocation, and now I'm left with 1 butene. Now likewise, I can take water and remove one of the blue hydrogens, and in that process I get both trans and cis 2-butene. So trans 2-butene and cis 2-butene. And if I look at the product distributions, according to Zaitsev, the more substituted alkene is going to be the favorite alkene. Why? Because it's the most stable. Well, notice trans and cis 2-butene have the same substitution. But as we learned prior in a previous chapter, trans alkenes are more stable than cis alkenes. And so we get the trans 2-butene as the major product. That's the one that we would expect to see. And as a matter of fact, that is the major product. And if you look at the product distribution of these three alkenes, you see 50% trans and 30% cis, which means that only 20% of the 1-butene is made. But notice, I get all three products, right? So I get all three products in this particular reaction. So that is the dehydration of an alcohol. You see, alcohols can be used to make alkenes. So alcohols can be used to make alkenes when they react with an acid like sulfuric acid or phosphoric acid. So make sure, when you're writing out your notes, your reaction notes, that you keep that in mind. Alcohols react with sulfuric acid or phosphoric acid to produce alkenes. It's a great way of making alkenes. So we see that we can make alkenes, we're going to see we can make alkenes in a number of ways, right? With alcohols or with anything that has a good leaving group. All right, so let's take a look at some examples. Here I have a tertiary alkyl halide, right? So I have one bromo, one methyl pentane, and it's reacting with methanol. One of the things that you have to always say is, what are the reaction conditions? So methanol is a very weak base. We're going to see why that's important a little bit later on. And I have a tertiary alkyl halide. So I would predict SN1 substitution. Now, if SN1 substitution is going to occur, I'm also going to get E1 elimination to occur. So what can I expect? Well, oftentimes when I do problems like this, I do one and then I do the other. And then I think about, okay, what's going to be the predominant product? So let's take the elimination product. Since we're talking about E1 elimination, let's focus on elimination products. What products should I expect to see? Well, in order to kind of figure that out, I have to think about the beta carbons. And notice the alpha carbon here has 3 beta carbons. Now, 2 of them are the same. So notice there are 2 methyl groups coming off of this alpha carbon, and therefore both of those methyl groups would give me the same product. And then there's a propyl group coming off, and it would give me a different product. So I think about elimination. I'm removing a beta hydrogen and the bromide is coming off, and I'm forming a double bond in between the alpha carbon and the beta carbon. Never anywhere else. So keep that in mind. So what do I get? Well, I get this product. So 2-methyl-1-pentene. 2-methyl-1-pentene. That's if I remove one of the beta hydrogens from a methyl group. Now, I can also remove a beta hydrogen from that propyl group, and I get this product. Right? So here I have 2-methyl-2-pentene. There's no stereochemistry in either one, so I don't have to worry about cis or trans, but I always should be thinking about that. Can I have cis? Can I have trans? Or EZ? And in neither one of these can you have that. So these are the 2 alkenes that I can produce. Now, what is my substitution product? So if methanol behaves as a nucleophile, again, I'm going to get carbocation formation, so always carbocation formation for tertiary alkyl halides, and with a weak base. And so now the product is going to be an ether. So I get these 3 products. I get my E1 elimination alkenes, and I get my SN1 substitution ether. Now, to evaluate which one is going to be favored, oftentimes I'm going to have to look at something else, like temperature, for example. If I have a low temperature, usually room temperature or lower, I'm going to the substitution is going to predominate. If I have higher temperatures, maybe 50 degrees or something like that, then the elimination products are going to predominate. Of course, I'm not given a temperature, so here I would simply say, okay, I'm going to get these 3 possible products as my product, as my distribution of products. Now, I do know that of the 2 alkenes that form, the product in the middle is going to be the dominant alkene. Why? Because it is a tri-substituted alkene versus a di-substituted alkene. And that's how you work on problems with E1 elimination, right? So let's look at another example. Here we have a tosylate, right? How do I make tosylates? I make tosylates from alcohols. And in this reaction, we're going to react the tosylate with ethanol. So again, you think SN1 substitution. I have a secondary alkyl tosylate. I have ethanol, so this is a solvolysis. So that's what makes me think of an SN1 mechanism. And of course, if I have an SN1, I'm going to get an E1 mechanism as well. Now, what do? I evaluate both products. So I look at the E1 and I say, how many beta carbons do I have? Well, in this particular case, I have 2 beta carbons. So what happens when the tosylate comes off and the beta hydrogen is removed? Well, if the beta hydrogen on the left is removed, I get this. But notice in this example, I can have cis or trans. So this is the trans, and of course I can also have the cis isomer. And sometimes it's just easier to write, if you have cis and trans, you can just write cis/trans, right, for simplicity. Because that will certainly show that you understand that both of them can form. So those 2 products form from the elimination of a beta hydrogen on the left-hand side of my reactant. Now I can also get another elimination product, eliminating a beta hydrogen on the right-hand side, and I get this. So notice this is a monosubstituted alkene. The 2 above are disubstituted alkenes, so they're going to be favored over the monosubstituted alkene. And those are my 3 alkenes. Now I look at substitution, and the substitution product again is an ether, an ethyl ether, and we get this. Again, we don't know which one's going to be favored. We do know that of the alkenes, the trans alkene is going to be favored. And both the cis and the trans are going to give the highest yields of my alkenes. That is how we tackle looking at E1 mechanisms. Now, we have to understand what promotes SN1 and what promotes E1. If there's a reaction that promotes SN1, it's also going to promote E1 as well.